Okay, let's talk about category 6. Woohoo! This is properties of rational functions. This is the section that we all loved so much. So let's get right into it. We're going to start with the basics. We're going to use quotients of polynomials. So basically we're talking about fractions here, where we have variables in the denominator, to describe graphs of rational functions, predict effects of parameter changes AHK, describe limitations on domains and ranges, and look at asymptotic behavior. So the real basics here, if I have a graph, I want to be able to write an equation. And so having looked at conics a little bit, maybe that has helped some in kind of seeing the asymptotes along here. This is oriented differently than it would be with conics, but I have an asymptote breaking my graph up right here. And I also have one breaking my graph up right here. So where those asymptotes meet is kind of like my center. That's my HK right there. So my H is -2 and my K is 0. And then for this one, then to check our A value, we're going to pick a point. So we're going to use this point right here, -1, 1. And that's going to be our xy. So we can use that to find our A value. So our function then, I'm writing it in calculator terms, f1 of x. We don't need all that. F of x is equal to A over x minus h plus k. And so then f of x is y. So I'm going to set up an equation. So I've got y1 is equal to A over my x value minus my h value plus my k. And then I'm going to solve and find my A. So 1 is equal to A over -1 minus a -2 becomes just 1. So for this particular function, A is 1. So then my equation is f of x equal to 1 over x minus h. So remember, h always does the opposite, so this is going to become x plus 2, and then I could write a plus 0 out here for my k, but I really don't need to. And that is the equation for that graph. Or given the equation, I need to be able to graph this. So first of all, I look right here at my vertical asymptote. Vertical asymptote is an undefined point in the graph, and on this point it's going to be at 1. So at 1, if my graph were ever to touch the x value 1, my graph would be undefined because 1 minus 1 would give me a 0 in my denominator. So my graph cannot touch this line. That's also my h value. So at it's going to shift then to the positive. So at +1, -3, that's kind of the center. My graph is moving around. And my A value is 1. So then I can sketch my graph and it's going to look very similar to this one here. But instead of being centered around the point that one was, this one's going to come down and be focused around this point. Not a wonderful drawing, but you get the idea. And of course, if it's in its equation form, we have calculators and we can graph that as well. Okay, so the other thing we talked about in asymptotic behavior is that we can also have removable discontinuities, or what we also call a hole in the graph. It's not always an asymptote breaking it up. So basically, both asymptotes and wholes mean that there is an undefined point, so there is some value in my denominator that can be made 0 there, and I can't have a 0 in the denominator. So I'm not going to work through these examples. I've included this worksheet in your review pages along with the answer key. You're going to factor algebraically if something in the denominator cancels with something in the numerator, then that's just a hole in the graph. If something in the denominator doesn't have anything in the numerator to cancel, then it's going to be a vertical asymptote. And we will use our graphs to check and see, because at an asymptote your graph should be breaking into two different parts, like so, broken apart, where with a hole in the graph you're never going to see it anywhere except on the table where it says undefined. We can check those by looking at the table for undefined. We can check it by graphing the denominator and looking at where the denominator crosses the x-axis as well. I'm going to let you practice that on your own. Some ways we've seen this earlier this year. So this pulls in our parameter AHK along with domain and range. So if I have this graph right here, so right now my center is right here, because my HK are going to guide how this moves. It's translated 3 units to the left and 3 units up. So I'm going to go 3 up, 3 to the left and 3 up. So my new graph is going around this point here. And this is, okay, what is a reasonable domain and range for this? So my HK is now at 2, 3. So when I write the domain for this, set of all x's, such that, first of all, I'm going to say that x is in the set of all real numbers. And it includes all real numbers, except, in this case, I have one undefined point, and that undefined point, and my transformation is right here, where h was. H always goes with my x. So x cannot equal 2. My range is going to be a set of all y's, such that y is in the set of real numbers, but y cannot equal my k value, or 3. So for rational functions, if you can find your hk, you also know where your domain and range are going to surround, or those points that they cannot include, so they'll line up with your h and your k values right there. In my original function, I would have said that the domain could not include 5 instead, and the range could not include 0, but it's been moved. Okay, and then we look at various representations. So I'm not going to do a lot with this. It's basically, you have your algebraic, your equations here. You have your tabular, undefined right here. That's going to be where your vertical asymptote is. And you have your graphical. And then there's also some about horizontal asymptotes here. And I've also included this worksheet in your review pages. So if you want to go look at this, the answer key is with it. So go through, work through it, look at the answer key, see how comfortable you are with this. A lot of it's going to be based on just analyzing. That's why that verb is underlined there. Looking at your graph, looking at your table, analyzing what's happening here. And also recognizing that this is h, and then k is out here, so you've got -3, 0 for your hk, and so that's going to affect your asymptotes. And then we'll move on to solutions using graphs, tables, and algebraic methods. So I'm going to do the same problem in as many ways as I can here. And so solving algebraically, basically when you are working with rationals, in some form you're going to be able to do a proportion. Some of them will be a little more complicated, like have plus or minus out here, and in those cases we would want to use graphing because we're talking about a timed test and we want speed here. But algebraically for this one, I can set it up. It's a proportion, so I can cross multiply here. So I'm going to say 4 times x minus 4 is equal to 7 times quantity of x plus 3, and I will distribute. So 4x minus 16 is equal to 7x plus 21. And I'm going to move my x's to this side, so when I bring my 7x over it becomes a negative, so I have negative 3x now. I'm going to bring this 16 over here, so that's going to equal a positive 37. And then I'm going to divide, so x is going to be a negative 37 over 3, which is approximately negative 12.3, the decimal. Things I need to consider here: restrictions. X cannot equal negative 3, and x cannot equal 4, because if it were equal to negative 3, I would have an undefined function here, and if it were equal to 4, I would have an undefined function here. So if I were to get those answers, I would throw them out. The least common denominator, and we would use this if we needed to combine our terms or to simplify them in some way. So your least common denominator would need to represent everything in your denominators. And so working in class, we looked at these and we said, okay, I have the x plus 3, what did I need here? Well, I needed the x minus 4, and we worked through those. Graphically, you're going to get the same answer. So graphically what I did is I divided this up, and in my first function I graphed everything that was on the left side. In my second function I graphed everything that was on the right side, and I found the intersection point. In the intersection point, the x value is negative 12.3, which is the same as here. Using a table wouldn't be very effective here because my answer happens to be a decimal, which means it's not going to show up in the table, and I wouldn't have a clue how to change the steps to make that show up. I could get an estimate, so I would be able to tell that it was somewhere in between or around negative 12 looking at the table, but I'm not going to be able to get an exact match that way. If it's a whole number, then at the table I'm looking at where my y values are the same, and I can find it that way. Inequalities, and we really hated these because they did take a lot of steps. This one isn't terribly complicated. Some of them get a little more complicated. So rational inequality, we're doing this graphically, and tables are helpful sometimes, but again, only when it's a whole number. So what we do is we graph what's on the left side. So I've done that. I've graphed this rational function that was on the left side, and then I graphed the line just 0 that was on the right side here, and I found the intersection point. And so we're going to show this on the number line, and then we're also going to write out the solution. Okay, so I know at negative 3 I have a closed circle because my inequality had the equal sign with it. But that isn't the only point that I need to mark here. I also need to mark down my restriction. So in this case, x cannot equal 5, because that would make my fraction undefined. So at 5, I need to mark my restriction here, and I'm going to use an open circle for that because my graph cannot touch 5. That's actually going to be the vertical asymptote. So that would be undefined. When I graph this, if I pull up my table right here, that would be an undefined point. Then I'm going to pull a test point here. So this is at 5. So I'm going to use 6 as a test point. And something in here, so we could use 0 as a test point, and then something here, so say negative 4 as a test point. And I'm just going to substitute in here and find which one is true. For this particular one, what I should get is this area in here, this is going to be where my true statement is. So when I write the answer out, then it's going to be negative 3 is less than or equal to, closed circle, x, which is less than, open circle, 5, and that would be my solution right there. Determine reasonable, big word here, this is the important one, domain and range values of rational functions, interpret and determine reasonableness of solutions. So basically you want to establish a reasonable domain and range in a situation so that you know that if you get an answer that's outside of that domain and range, you're not going to use it. So in this situation, this is science here, chemical compounds concentration can be modeled by the function below. T represents the number of seconds that have elapsed during the reaction. This was taken from a previous EOC test, so this is one of the ways you could expect it to show up. So my function is given here, and I have graphed my function, and of course I've changed t to x because I can't graph a t. And so this is what my function looks like. I also pulled up the table because I'm interested in when x is 0, what my y value is, because I'm looking at this range here. I'm wondering where that 100 came from. So the 100 comes from, at 0 I'm at 100. And so then I'm looking at how far down is this going to go. And so analyzing my graph, I can see that it's leveling out at 0, but just common sense here, if we think about concentration and a chemical compound, there's no way that chemical compound is going to get below 0. So my range and my y values here, this is range, is beginning at 100, and it cannot go below 0. So I'm looking for a range that matches that. So this range and this range would match that. So this is not my answer, this is not my answer. So then we're going to look at domain. Domain is my time in seconds. And so again, in this situation we know that time cannot be negative, so I'm looking for something that says only use this portion right here. So this one says has to be greater than or equal to 0. So this is the domain and range that would be reasonable for my situation. So the portion I'm using of the graph is only the first quadrant, and even then only up to 100, not even all, because this would continue on forever upward. But I'm only looking at 100 in the situation. So any answer choices that I have and any questions that they gave me, if they don't fit into this domain and this range, then I would throw them out because they don't make sense. Alright, and in this category also we saw direct and inverse variation. I'm not going to go into direct variation because that's a linear function, and we've already talked about that in other categories. Inverse variation. The good thing about inverse variation is you can generally figure the answers out algebraically if you just do a little bit of math. But sometimes they set them up to look like a proportion, and you can't use proportions with inverse variation because there's more to it than that. So these are generally signified by the word inversely or varies inversely or something to that effect in the question, and we're going to set it up just exactly the way it's read in the same order. So in my equation I have y equals, so the first thing I come across is going to be y equals, so the cost per person to rent a chartered bus varies inversely, so equals the number of people who ride the bus, and so that's going to be my x. Varies inversely, inversely meaning it's a fraction, so first of all I need to find this value here, so we're going to set up what we know. Okay, so here's my equation. So the cost per person to rent a chartered bus varies inversely to the number of people who ride the bus. So the cost per person is $9.50. So I need to find out how much that is then if 40 people are going. So to solve for k, I'm multiplying by 40 on each side. So any top, any bottom. So I'm going to multiply these out. So 950 times 40, 0, 4 times 5 is 20, times 9 is 36, so $380 for 40 people to go. So then I want to know, so there's my k, how much would that cost for 25 people? I've got 380 divided by 25, goes in there once, remainder of 15, and go in there 5 times, be 125, remainder 5, and 2, so So $15.20 should be the cost if only 25 people vote. But once you have this, yeah, you're going to have to work through this. It's not going to be one that you can just graph in your calculator, find the intersection point. These problems, however, and this is our readiness standard, and this is the only readiness standard in this category from which 5 questions are being taken, so you can expect to see a few problems where you're having to formulate equations and analyze. So I went with the basics of what we covered in class. It's really hard to predict what they're going to use or how they're going to present this. And so we're going to do work problems, we're going to do distance problems, we're going to do a percentage problem. And so when we're talking about filling or emptying anything, we're talking about work. So work is always alone, and alone equals together. And so depending on whether we are filling or draining this tub, will determine whether we are adding our alone and lone or we are subtracting. So in this particular situation, we are filling and then we are emptying. So we want to know how long this is going to take. So I can fill one tub in 16 minutes. And I can empty a tub in 20 minutes. So it's emptying. It's negative. How long would it take me to fill the tub if I forgot to put the plug in? That's the question here. And so I got some really creative answers on this. This was on a test, and I had a lot of people tell me, well, it's never going to fill because it's emptying at a faster rate. But no, it will eventually fill up. It's just going to take quite some time. I'm not going to go through and do the solution to this, because basically once you have it set up, the fastest way, because we were looking at select a method and solve problems, we're talking about how to do this efficiently. So we would graph this side and graph this side. You're going to have to zoom out quite a ways, find the intersection point. We will not use any negative intersection points here, and we're not going to use nsolve here because there could be 2 solutions, often are 2 solutions, and the first one it will pick up is the negative value, which won't work for you. So we're going to use graphing to solve this. It's the best method here. The work problem here is the same way. Carl can do a job, so he completes one job in 4 hours. This is Carl. Mike can do the same job, so Mike completes one job in 6.5 hours. Together, so they're working together, not taking away from one another. How long will it take them to complete? So same job, X amount of time. We're going to graph this side, find the intersection point. And then these lovely distance problems here. Motorboat is going 36 miles upstream on a river whose current is running at 3 miles per hour. The trip up and back takes 5 hours. What is the speed of the boat, assuming that it maintains a constant speed relative to the water? So we're going to create a ratio for upstream and then another one for downstream. So it's going to be distance over rate equals time. And that's just a variation of your distance equals rate times time formula. So we're just going to input here. So it goes, so let's do upstream first. Upstream, 36 miles. And so we're trying to find the rate that it's traveling. We don't know. But if it's traveling upstream, we do know that the current is going against the boat. Then it's going to come back downstream, so it's the same distance downstream. Now you could have a problem where it's a different, they didn't come all the way back, but it's always going to be how far they went up here, and then how fast they went down here. So I have the same rate for my boat, assuming it maintains a constant speed, but this time I'm moving downstream, so the current of the river is actually helping me along here. And together, those 2 parts of the trip took 5 hours. And so we'll do the same thing here. We're going to graph the left side, we're going to graph the right side, find the intersection point. So you can practice doing that. Then percentage problems like this, you can actually figure out algebraically if you'll just, well, not algebraically, just simple math. If you'll just set up a ratio and then keep going until you find the right percent. The football team has a record of 9 wins and 12 losses. So right here is where most of the mistakes took place. If I'm setting up a ratio, I want part over whole. So we're talking about, we want to know about wins. So they have won 9 games, but it's not 9 out of 12. It's 9 out of 21 because there were 12 losses. So that means they played a total of 21 games. And I want to know how many they have to win in order to raise their winning record to 50%. Well, I could say, okay, they play another game and they win. Figure out what that percent is. They play another game and they win. Figure out what that percent is. They play another game and they win. Figure out what that percent is until I get 50%. But that's going to take a long time, and we're talking about ways to do this quickly. So the pattern that you see here is that this is increasing by the same amount every time. So instead, I'm going to set up a problem that looks like this. So whatever I add on the top, I'm also going to add on the bottom. And then I'm going to set that equal to 50%. And I'm going to graph this side and graph this side. And so 50%, I think you're actually going to have to multiply that by 100 in the end. And again, don't use NSOLVE here because you're going to have 2 places most likely where this crosses this. And so it's going to pick up the -1 first, and that's not going to fit your situation, and chances are you'll write down that answer and then you'll get it incorrect. And that's about it for category 6. That leaves us with just one category, and it's really not a bad one. It's going to be our logarithms and exponents. They're all in one category together, and there's only a total of 6 questions out of that category. So we've about got it covered. Like I said, I'm posting review worksheets in Edmodo for you to practice these problems. Bring them into tutorials or into class if you have any questions of them.